上中线老师要演讲，然后那个下礼拜演讲不会公告，然后但是还是会给你这样，然后之后晚点还会再继续提醒你们可能已经收到指出消息，有智商中心，下礼拜智商中心发表了。好，那我们今天很高兴请到中央研究院的王以晟博士。那他今天要讲的东西是 Entanglements, Classification, Symmetry, and Application。
Thanks, Professor Liao, for the invitation. I'm very glad to be here. I think it's the first time I give a talk at the Tsinghua University, and also my first colloquium talk, I think. And yes, for today I want to talk about entanglement. Especially I want to talk about how to do classification, how to measure their symmetry, and also some applications of the theory of entanglements in some real-life problems. So I will start with handle-body links. That will be the main objects, the main entanglements object that we are interested in, and then I will show you how to classify the handle-body link using enumeration or tabulation, and then I will introduce the notion of symmetry group. This can be used to measure symmetry of a handle-body links or handle-body knots. And the last part will be the application part. So let's begin with handle-body link. So what's a handle-body knot or handle-body links? So before I give you a precise definition, let me first recall what is a handle body. A handle body is something very simple. It's a 3D object. It's a 3-ball with some 1 handles attached. So it's a 3-dimensional object. And as you can see, there is a genus 2 handle body because you have 2 handles here. It's topologically equivalent to something looks like a handcuff. And this is a genus 1 handle body because you just have 1 handle, and it's equivalent topologically to a solid torus. Okay, so that's clear. That's what we call a handle body. And a handle body link then is a embedding of finitely many handle body in an oriented 3-sphere. So this is an example. This is a handle body link. It has 2 components. One is of genus 2 because there are 2 handles, and the other is of genus 1. And if you just have 1 component, we also call it a handle body knot, and this is an example. So you just have 1 component, and it's knotted. It's embedded in a 3-sphere in a knotted way. In the case that you have a genus 1 handle body knot, then it reduced to classical knots. A classical knot is just a circle in a 3-sphere, a knotted circle in a 3-sphere, and that's because you can consider the spine or the skeleton of the solid torus or the core of the solid torus. Then you get the classical knots. Okay, so is the definition clear to everyone? And for today, I will be focusing on handle body link with exactly 1 genus 2 component and no other higher genus components, because we want to generalize the classical knots. So we want to consider handle body link with at least 1 genus 2 component, and we want to. It's also okay to consider R3, and the main reason that I consider as using 3-sphere instead of R3 is because it's compact. It's compact, and when you do topology, you like to have your space to be compact, then you can have better control over it. Right. So the reason that we don't want to consider components of higher genus, they are interesting also, but we don't want to make it too complicated. So for now, we just consider handle body link with exactly 1 genus 2 component. And this is an example. And this is also an example. It has another component, but it's genus 1, so it's okay. All right, so that's the main object. And what we want to do is to do classification. We want to classify them up to equivalence. And this is the definition of equivalence. If 2 handle body links are equivalent, 2 two handle-body links are equivalent if one can be deformed continuously into the other. And there is a series of deformation illustrated here. On the left-hand side, you have a trivial knot, trivial handle-body knot, because it's nicely embedded in the 3 space. It's not knotted. But on the other side, you have something look like it's knotted. See that? So they appear to be different, but when you look more carefully, you see that there is a series of deformation. You see, you can move this leg a little bit to the left, and then you move it across the saddle point, move it down, and pull it to the right, then you get something like this. So even though they appear to be different, but there are deformation that make one into another. So they are equivalent, actually, by our definition. And if you want a more precise definition, you can also think of it as having an orientation-preserving homeomorphism from the 3-sphere to itself and sending one handle-body link to another. So that's another way to define it. They are equivalent. Okay? And our goal is to do classification, to classify handle-body links up to equivalence. As you can see, that it's not always easy to see whether two handle-body links are equivalent or not, because there are too many possibilities to deform it. As long as you don't break it, as long as you don't tear it, then it's all allowed. But it's difficult in general. Why? Because there exists some chiral objects. So what's a chiral object? It's not something complicated. That's something actually you probably encounter quite often every day. So look at this picture. There is a mirror, and in front of it there is a handle-body link, and inside the mirror is its mirror image. And we ask the question whether this handle-body link is equivalent to its mirror image. If it's not, then we call it a chiral handle-body link. Okay? So that's clear. And the reason that the classification problem is not easy, one reason is that detecting chirality is usually not very simple. And just to give you some examples, there are some handle-body knots with small crossings. They are not complicated handle-body knots because the crossings are not so, there are not many crossings. But nevertheless, their chirality are still unknown. Okay. So in view of this, we divide our classification problem into 2 steps. The first step is to classify them up to mirror image. So at the first step, we don't care about whether it's equivalent to its mirror image because detecting chiralities might not be easy. So that's our first step. And if we can achieve it, we then try to determine their chirality if possible. Okay? So is everything clear so far? It means that I don't care, first of all, I don't care that whether it's equivalent, whether it's a chiral object or not. So it can be equivalent to this mirror image, but I still consider it as the same. So I mark out a weaker equivalence, so to speak. Yeah. Yeah. I wouldn't say it's really easier, but there are more invariants available. So for classical knots, there are more invariants like Jones polynomial, Kaufman polynomial, and other topological invariants that can help us to distinguish different knots. But for handle-body link, handle-body knots, there are fewer invariants, and sometimes they are very difficult to compute.
So is there a knot whose equivalence with its mirror image is then determined?
For knots, I don't know. I think most of them are now determined because Jones polynomial, for instance, are very sensitive to chirality. Yeah. I think there are there are two knots that are very difficult to determine. One is of crossing number A, another is of crossing number 10, and some people use Chen-Simons theory to determine the chirality. So it could be hard, even in the case of knots. Does it answer the question? Okay, thank you. Okay, and so that's our chirality problem. So that's why we have to divide our classification problem into two steps. But how do we do classification? So we do it by enumeration. We enumerate the handle-body knot from the simplest one to more complicated ones. So when I say this, you might ask, what then do you mean by more complicated? We need to know how to measure complexity. So let me just give you two examples. Which one do you think is more complicated? Well, I would say the one on the right-hand side. But you might have different opinion, right? We have to have a definite way to measure complexity in order to do enumeration. And there are many different ways to define complexity. And for today, I would like to use this crossing number. I should say, for the classification problem, we will use crossing number to measure our the complexity of the handle-body links. So that's the definition. It's very intuitive. So here we have a handle-body link. You consider the spine of the handle-body link, and then you project it to the two-dimensional space. Of course, you will get some intersection, and you replace this intersection using this broken arc diagram. And it means that the unbroken part is above the broken part. And in this way, you can restore the original handle-body link. And we call this a link diagram. And we call this a crossing. So you can count the number of crossing, and that will be the crossing number of the diagram. But for handle-body link, there are plenty of projections. You can project it from the right, you can project it from the left. So there are many different kinds of projection. So in order to have a well-defined crossing number for handle-body link, we have to consider the minimal of the crossing number over all possible diagrams. So in general, it's not easy to compute the crossing number. But you will see that in the case of small crossing number handle-body link, it's possible to compute. Okay, that's the example. So for this case, the crossing number is 4. For this case, it's crossing number 6. Well, if you are very careful, you might say, well, you are wrong, because there are 5 crossing, 1, 2, 3, 4, 5. And the reason is that this is not a good projection. If you move this part to the right, to the left along this loop, then you get a 4 crossing diagram. It's not always easy to find the best projection. All right, but that's our complexity measure. We are going to enumerate handle-body link based on crossing number. Another thing that we should note when we do classification or when we do enumeration is that we don't enumerate everything. We only enumerate irreducible objects. And it's just like number theory. We are mostly interested in prime numbers, not just any number. Because any other numbers can be decomposed into a product of prime numbers. And so is the case for handle-body links. If we can enumerate irreducible objects, then we can also obtain other reducible objects. So that's the definition of irreducible handle-body links. They are handle-body links that cannot be decomposed by a two-sphere. And so this is an example. Here we have a handle-body link, and there is a two-sphere, and it can be decomposed into 2 non-trivial parts. And that's why we are not so interested in reducible handle-body links, because they can be obtained by irreducible ones. And when you do enumeration, you want to save your resource, so we only enumerate irreducible object. The definition might look simple, but to detect irreducibility could be difficult, could be challenging. And this is an example. This is a reducible handle-body knot. But can you see the two-sphere? Any idea? Anyone? Well, the thing is that the two-sphere can be highly deformed. It's there, but you cannot see it right away because it's highly deformed. So anyhow, there are two things. We do enumeration, we do classification by enumerating handle-body links based on crossing number, and then we enumerate only irreducible objects. And the result is the following table. So that we obtained last year. So it's a small table, but you already take a lot of work to complete it. We start with the simplest one, which has 4 crossings, and go from something more complicated. It's, as you can see, there is another one with 5 crossings, and the rest is of 6 crossings. And this is a complete table up to mirror image, in the sense that if you happen to have a handle-body link and you compute the crossing number and you realize that it only has 6 crossings or less, then it must be equivalent to one of the entry in the table up to mirror image. So this is a complete table. Okay, so I'm going to show you the ingredients that goes into the construction of the table. But before that, I would like to give you a historical remark, because the knot tabulation has a very interesting history. So knot tabulation for classical knots, it already started in 19th century by Tate, who is a physicist. So he's not a mathematician, but why was he interested in knot tabulation? Because at that time, motivated by Kelvin's vortex theory, they think the periodic table that you see in chemistry made of knots, not elements. And that's why they start to do knot tabulation. Of course, they realized later that this is not the right direction. But mathematician has already got interested, and they took out the job, and they continue to do the enumeration, and now prime knots up to 6 crossing are all classified. The prime knots are just something like irreducible handle-body knots. Knots that cannot be decomposed further. And there are more than 1 million knots, so you need a computer to help you to do the classification. But that's all about classical knots. For higher genus handle-body knots, genus 2 handle-body knot table is just constructed in 2012. Maybe I can show you. Okay, so that's their table. It's also up to 6 crossing, not very big. But again, it took a lot of people's works to complete the table. Again, you see it start from the simplest one to something more complicated. And for handle-body link, it was built last year. Okay, and that's the table you saw earlier. Okay, now let's have a look at some ingredients of the construction of the table, because we have to use some theories from other fields. And the first is graph theory. And why do we need graph theory? Yes, yes.
But in the definition, you define by like integrating
A 3-dimensional thing into 3-dimensional thing. A handle body is a 3D object. But because we always see the projection, so it looks like it's 2-dimension, but actually it's 3-dimension. We just represent it. There are different representatives. This is one representative. We just represent it because it's more complicated to draw the solid object. But if you have something like this, just fatten it, then you get a handle-body link. You see, it looks like it's a skeleton, and as long as you have a skeleton, you can recover it. So you can obtain a different table with different representation, but it must be equivalent to some of them. Yeah. Oh, that's a very good question, and that will give you different objects. That's called spatial graph. The thing is that when it's a 3D object, these two trivalent vertices can swap. You can swap them. You can then go very, very close, and then you suddenly swap them. This is okay in 3 dimensions, but it's not okay in 1 dimension. because you want to preserve the graph structure. Yeah. All right. But still, it's very close to one-dimensional things, and that's what I'm going to talk about. We have to use graph theory, and because our idea is that in order to enumerate handle-body links, we first enumerated the link diagrams, and in order to enumerate link diagrams, we enumerate the associated planar graphs. So what do I mean by this? So here we have a graph. It has 2 trivalent vertices and 4 quadrivalent vertices. And we replace the quadrivalent vertices by crossings like this. And that way you get the link diagrams. So in other words, if you are able to enumerate planar graphs up to certain number of quadrivalent vertices, then you will be able to enumerate link diagrams up to certain crossings. So the idea is very simple, but there are plenty of such planar graphs. So it's still difficult to do it, but we can ask a computer to help us by translating the graph, the planar graph, into a matrix. So you see, 0 is the first row, and we just go around the vertex counterclockwise, and you get 1, 6, 7. So here we have 1, 6, 7. And for the vertex 1, you do something similar, so you have 0, 5, 4. So it's up to permutation, but it's okay. As long as we can write it down as a matrices, as a matrix, then you can ask a computer to do enumeration for you. And the result is a list of a very long list of planar graphs or link diagrams. A lot of duplication, a lot of reducible objects, and we have to get rid of these illegitimate objects. And because of this, we need algebraic topology and graph theory. The goal is to construct strong non-invariant to make sure every 2 entries in the table are in equivalence, and none of them is reducible. And better still, we can determine the chirality of all of them. So in contrast to the case of handle-body knots, the chirality of the handle-body links in the table are all determined. But as you can see, by the way, I should show you what kind of invariant we are interested in, because the professor has just asked that the difference between classical knot theory and handle-body link theory. One big difference is that we don't have many polynomial invariant in handle-body link theory. But in this case, we still can consider fundamental group. So this is a handle-body link. It has 3 components. We can consider its complements and consider fundamental group. But this is too weak. We have to consider a diagram of a fundamental group. And using this, we can construct some computable invariant that are able to distinguish all the handle-body links in the table and even determine their chirality. Okay. But the computation load is heavy, so we need to have computational topology comes into play. We have to implement the algorithm into a code in order to run with computer. All right, so that's about classification. Oh, it's already 25 minutes, but still, I want to have a break in the sense that we can do some puzzles. So I prepared something. Can you hear me? Good. I don't know, maybe some of you have already seen it. If you do, then don't just give it away. So there are 3 loops. 1 trivalent vertex here. There are 2 smaller loops, which I'm going to put it around my hands. And there is a bigger loop down here. Now what I want to do is that I want to make a tangle. Let me see, maybe I do it like this. Okay. Now I think it's really knotted. Can you see that? Okay, everybody see that? So it's knotted. Now the question, the problem is that, are you able to untangle it without moving these 2 loops of your hand? Is it possible or is it not? Proof is proof. Any idea? Anyone? Or anyone want to try? very shy. Well, the answer is yes. Somebody wants to try? You? Come here, if you want to. I can put it around your head. Okay, the answer, okay, maybe you can try it later, but it's very easy to make. Anyhow, I will show you it's possible to untangle it, and I'll show you how. So I pick a piece, and I put it around my wrist, and put it over the white loop, and put it back from underneath. So the white loop is here, and I put it off my hand, and let's see what happens. It's still not it, unfortunately, but let's do it again. Let's do it again. Let's do it with this. The same trick, I put it over my hand and then put it back from underneath of the white loop. And then I still can untangle it. That's not quite a way. Let's do it again. Now I really untangle it. You see that? So it's possible to untangle it, but what I want to show you is that the number you need to untangle it is another way to measure complexity. You have seen a complexity measure using crossing number, and another way to measure complexity of entanglement is to count how many times you need to apply the tricks. For instance, if you do something more complicated, then you might have to use a few more times the same trick. Let me try another one. So that's another entanglement. I don't know if it's yeah. So this is again an entanglement. I will do the same thing. I will just play the same trick, and then I'm a bit confused. Yeah, I just play the same trick and see how many times we need. Maybe just one. Okay, you see, it's still get entangled, but we can do it again. Maybe I do it here. Now it's untangled, I hope. It's not, so we have to do it again. Yeah, that's unfortunate. I want to show you that two tangles might require different numbers of times that you have to apply different numbers of times of the tree in order to untangle it. But I just want to show you that is another way to define complexity. And there is another interesting story that I want to show you, and that's a puzzle which is called possibly impossible. So there are two pieces. One is the green part, and the other is the white part. And the problem is that are you able to free this white loop from these pieces? And this is a puzzle designed by Stephen Copy. It's a much more difficult puzzle than I want to show you, and you will see why. It was designed around 1970s. And what's interesting is that after he made the puzzle, he was not able to solve it himself. So he started to wonder, is it solvable? Is it really solvable? But what's more amazing is that after he published the puzzle, some people say, yes, it's solvable, and even at least one solution is published in the book. But as you can see, there are too many possibilities. You can pull this loop around another loop, you can pull it up, you can twist it. So there are just too many possibilities. So the solution is very, very complicated, and people just cannot verify it. So it remains a difficult question. It remains a difficult question for many puzzle makers. They are still not sure whether it's really solvable. And it's until 2003, a topologist proved that it's not possible. They use fundamental group. So basically, it's saying that don't try it anymore. You will never be able to free this loop. And they use algebraic topology to prove it. And I want to show you that it also follows from our link table, because this is exactly this one. If it would be solvable, this handle-body link wouldn't be reducible. But since it's irreducible, it wouldn't be irreducible. But since it's irreducible, so it's not solvable. Okay. All right, so let's go back to our serious mathematics. Symmetries. So we are interested in symmetries of handle-body knots. And what kind of symmetry are we interested in? Rotational symmetry, for instance. They are orientation-preserving symmetry. So imagine that there is an axis perpendicular to the screen, and then if you rotate the handle-body knot by pi, then you get back the same knot, right? So this is a kind of symmetry. Another kind of symmetry is orientation reversing. That you have already seen. That there is a handle-body link, and inside the mirror image. On the other side of the mirror, there is its mirror image, and we are asking whether they are equivalent or not. So more generally, you can think of a symmetry as a homeomorphism of S3 preserving the handle body. And if you collect all of these homeomorphisms, map out isotropy relation, then you get a group, which we call the symmetry group. So if you don't know what is isotope, it just says that two homeomorphisms are isotopic if there is a series of homeomorphisms, the same kind of homeomorphism connecting them. Then we call these two homeomorphisms isotopy. Okay, so together, just collect all these homeomorphisms together, you get symmetry groups. Of course, if you are just interested in orientation preserving symmetry, then you get a positive symmetry group, which is a subgroup of this group. And their relations are very simple. It's like the following. If the quotient is trivial, then the handle-body knot is chiral. Well, the thing is that if the quotient is trivial, then it means that there is no orientation reversing homeomorphism preserving the handle body, and therefore it can never be equivalent to its mirror image. And for us, the goal is to understand the structure of these two groups. We want to compute them, or at least, or even classify them. In particular, we are asking the following two questions. Is it a finite group? Or when is the symmetry group a finite group? And the answer is it's not always a finite group. But when is it a finite group? We will see the answer. And also, if it's a finite group, can we classify its group structure? And in the case of genus 1, both are answered at around 1990s. So we know that in the case of classical knots, when it's a finite group, and if it's a finite group, it's either cyclic or dihedral. But for the second question, it's only solved in 2020. I have to say that for the genus 2 case, it's split into two parts. The first part follows from Thurston's hyperbolization theorem, and the second part is proved by Funayoshi Koda in 2020. By the way, when I was in this part of the talk about handle-body knot symmetry, I'm going to focus on the connected one. I'm not talking about handle-body link with more than one component. So I will just be, for genus 2 case, I mean the genus 2 handle-body knots. So we don't consider link here. You can consider link here, but I want to restrict our attention to just handle-body knots. All right, but very little is known about the second question. We do not know about the structure of these finite symmetry groups. And that's what I'm very interested in right now. Okay, but in order to understand the second question, we have to first look at the solution to the first question. And that is the theorem. And basically it says that if you have an irreducible handle-body knot, then the symmetry group is finite if and only if it is hyperbolic or toroidal-cylindrical. So I'm going to explain what these three terms means, but basically it just says that it's finite if and only if handle-body knot is the following two types, hyperbolic or toroidal-cylindrical. And a hyperbolic handle-body knot is a handle-body whose exterior, so that's the closure of the complements, admits a hyperbolic structure. So it has to be a good hyperbolic structure. It's complete, it has a totally geodesic boundary. And what is toroidal-cylindrical? So these are two adjectives. The first one, toroidal, means that the exterior contains no essential torus. And let's have a look at the example. This is a handle-body knot, and you can see outside the handle-body knot there is a torus enclosing the handle-body knots, and it's essential because if you look at the torus alone, it's knotted. Can you see that? So that's why it's essential, because itself is knotted. And toroidal means that the handle-body knot, the exterior of the handle-body knot cannot contain any such essential torus. Okay, so that's toroidal. That's about non-existence. Now for cylindrical, it's a condition. It's an existing condition. It says that the exterior of the handle-body knot should contain an essential annulus, and this is an example. This is an essential annulus. You see, this is the handle-body knot, and this is an annulus nicely embedded in the exterior of the handle-body, and it's essential because you cannot compress it. This is an essential annulus because you can compress it. You compress it, you get two discs. And the same for this case, it's also an inessential annulus because you can compress it. And if you don't have these compressing discs, then we say it's an essential annulus. So go back to the theorem. He is saying that the symmetry group is finite if and only if the handle-body knot is hyperbolic or a toroidal-cylindrical, means that it doesn't have any essential torus but has at least one essential annulus. And for today, I'm going to focus on the second kind, toroidal-cylindrical handle-body knots. Okay, so in order to do the computation, is everything clear so far? Understandable? Okay, so in order to do the computation for the second kind of handle-body knots, I'm going to recall the classification of essential annuli. Okay. So the essential annuli are classified into four types by Koda and Ozawa in 2015. And the good thing about their classification is that they can be described in terms of the relation between the annulus to the handle body topologically. So that's an example. So that's I call it type 1. And type 1 handle essential annulus is characterized by the following property that you see there are two components. One component bound the disk in the handle body, and the other component doesn't. And this characterizes the type 1 annulus. And type 2 annulus looks like this. There exists a disconnecting disk in HK disjoint from A. So by the way, this is the annulus. It's twisted, but topologically it's an annulus. Okay, and this disconnecting disk is this green small disk here, and it's disconnecting because if you cut it, deform the handle body, and you get two solid torus. So before you have one component, and now you have two components, so it's a disconnecting disk. So these are type 1, type 2. Of course, we have type 3 and type 4, and they can be described similarly, but I'm not going into detail for these two types. Okay, but for type 2 annulus, let's have a closer look. If you just consider the boundary of the annulus, and you see there are two curves on the solitary, and they are twisted along the solitary. And how they are twisted can be described in terms of two rational numbers. I call it boundary slope. And for instance, this is a type 2 annulus with boundary slope -1, -1. It just means that the curve is twisted along the solid torus once and negatively. Okay? So that's the classification of essential annually. And with this in mind, I can show you some of the results. The first one is that if A is unique and unknotting and of type 1, remember type 1 is one that has exactly one component bound the disk in the handle body, then the symmetry group is trivial. Okay, but I didn't show you, I didn't tell you what is unknotting. And let me just show you an animation. And then you see what's unknotting. By the way, how can I stop it? I couldn't. Okay, let's do it again. So you see, this is the annulus, and then if you consider the union of the annulus and the handle body, and then you deform it, and in the end you get an unknot. And that's why we say this is the definition of an unknotting annulus. If the union of the annulus and the handle body is an unknot in the 3 sphere, then we call it unknotting. And if this is the case, then the symmetry group is trivial. And the second result is that is for type 2. If it's unique and of type 2 with boundary slope PPP is not 0, then HK is chiral, it's not equivalent to its mirror image, and the symmetry group is rather small. It's either trivial Z2 or Z2 cross Z2. And here are some examples. These 2 handle body knots, they all admit type 2, a unique type 2 annulus. And one has the symmetry group Z2 and the other has Z2 cross Z2. All right. There's something about the proof, but I think I will just go over it very quickly. We need mapping class groups of surfaces because the boundary of the handle body is a surface. We also need spatial graph theory because the spine of the handle body knot gives you a spatial graph. We also need 3-dimensional manifold topology because the exterior of the handle body knot is a 3 manifold. Okay. All right, so that's about symmetry. Any question? All right, if not, then let's have a look at some application of entanglement in some real-life problems. But before that, let me just show you a big picture of how topology can be used in data analysis. So in general, it's like that. You mean this one? Okay, the generator, right? Let me see if it's easy to see. Maybe not. Yeah, I think you do rotation against this axis. But for this one, it's more difficult because this is not a good right projection to see this. So there is one element which is rotating against this axis. And there is another one that cannot be visualized as a rigid motion here. Yeah, so that's another problem because when we have a projection, we are not always able to visualize them as a rigid motion in terms of certain projection. Maybe I can, if I remember correctly, this is equivalent to this one. 1, 2, 3. Oh no, this is an unknot. I think this is equivalent to this one. Now you can see you can do a rotation here. And you can also do a rotation here. So that would be the generators then. And that's a good projection, but this one is not. But on the other hand, it has 5 crossing. 1, 2, 3. It has 6 crossing. or 5. 1, 2, 3, 4. It has 5 crossings, but it has 6 crossings. So in terms of crossing number-wise, this is not a good projection. But as far as symmetry concerned, this is a better one. Okay. All right, so for data analysis, usually you get a point clouds or a matrix. And then the idea is that I want to use the properties of the data to construct a topological space or graph or simplicial complexes. Let me give you an example. Suppose there are 4 people. Person A knows person B knows person C, and person C knows person D. And A and D are also friends, so they have a circular. But A and C are completely foreign to each other, so there is a circular relation. But if A and C are also good friends, then you get a 2-dimensional relation. So you can use the relation between 2 data points to build a topological space in terms of their connectedness. And once you have a topological space, then you can use topological invariants, something like such as persistent homology, to obtain some quantitative information. And the quantitative information will give you, in turns, give you some way to analyze your original data. So that's the broad picture. But for me, I'm more interested in not just the topological space, but the entanglements between 2 clusters in the data set. So for instance, there is a data set, and you see there are 2 clusters of data, one in red and one in blue, and you can construct the associated complex. There are many different ways to construct the associated spaces. I just use this as an illustration. And as you can see, they are entangled. And then we might ask that how to describe their spatial relation, how to describe the complexity of the entanglement between 2 clusters in the data set. Okay, so that's still too abstract. Let me give you some examples. Suppose you have 2 particles on a plane, and they are moving. And because it's a 2-dimensional plane, so if you have a 2-dimensional plane plus time parameter, give you a 3-dimensional plane. And if you view the movements of this particle in this 2 plus 1 dimension, you get an entangled path. And these people call a braid. And many people are interested in this because, for instance, they are related to topological quantum computing. People working on topological quantum computing view particles on a plane as qubits. So they are degenerate ground state. They might have different history. And this entangled paths, on the other hand, is the logic gates. So different entangled paths represent different computation. And the good thing about topological quantum computing is that because it depends only on the topology of the braid, so it's highly protected from noise. Okay, so that's one of the main advantage over classical quantum computing. But topological quantum computing also has its own drawback because it's very difficult to find a material that realizes the topological quantum field theory. But theoretically, as far as efficiency concerned, it's very similar to the classical quantum computing. And there's another interesting application that I find recently. It's about crowd analysis or multi-agent interaction. So that's really closely related to artificial intelligence. I don't know if you can see, so this is a crowd. There are a lot of people in a confined area, in an area. And again, if you observe this crowd, they are moving. If you observe this crowd for a period of time, then you get an entangled path in 2 plus 1 space, so 3-dimensional space. Their paths might be entangled. It doesn't have to be people. It can be cars or anything that is moving on the 2-dimensional space. For instance, you could have a traffic scene. Maybe you have a satellite and you observe the traffic scene over a period of time in a certain area, and then you want to analyze the interactivity of this traffic scene. And why? For instance, you want to do autonomous driving or navigation planning, because when you have a traffic scene, you want to know how to interpret that. It Is the interactivity too complicated? Are they going to have? Is there going to have a traffic jams or things like this? It's very helpful to do navigation planning if you are able to interpret the traffic scenes correctly. And the brain invariance, so this is another kind of entangled invariance, is a good way to measure the complexity of the interactivity of a traffic scene, for instance. Of course, you can ask something more theoretical. We are talking about two particles moving on a plane, and it might not be moving randomly. It could move with certain distribution. For instance, the green one might tend to move to a certain area, and the purple one might tend to move in certain pattern. So they might not be moving randomly. And the question is that if you change the distribution, how are these tangle types going to be changed? And I just do a very simple experiment with two randomly moving particles just to show you how likely they get entangled when the distribution is a random distribution. Okay, that's the statistic that I get. I just do 50 times test. I run computer 50 times for two randomly moving particles. And you can see that the brown bar represents the number of tests which I get an untangle. So a trivial entanglements. So there are 9 out of 50, and the rest are all entangled, but more toward the left or more toward the right means that the complexity increases. So as you can see, that when the complexity increases, the number also decreases. But what surprised me a bit is that actually many of them are entangled. Only a few of them are unentangled. So it means that if you want to avoid entanglement, you cannot move randomly. Yeah. All right, so I think that's all what I want to present for today. Okay, it's also about the time. Yeah, so thank you for your attention.
？Can you give an example of infinite symmetry?
Oh, yeah, this toroidal one. That will give you. Okay, maybe I just use blackboard. So you mean the infinite one, right?
Yeah.
And actually, we have this this theorem that if it's an infinite group, then it's either reducible or toroidal. So in the case of, let's say we have a handle body now like this. Okay, this is a reducible one because we have a disk separating them. And now it has an infinite symmetry group because you can cut the disk. Then you decompose the handle body, also the exterior, into two parts. And then what you want to do is that you do a twisting 2 pi by 2 pi, and then you glue it back. And this is an element of infinite orbit. And the same thing happened in the case of toroidal handle body knots because it's difficult to draw, so maybe
Because you can do a 3-dimensional version of that twist.
Exactly. So that's the same with toroidal handle body. As those you can decompose into 2 pieces, and they are free loops, you can do that twist.
More questions? If there's no question, I thank the speaker again.